Dr. Eugene Boland, Chief Science Officer for Techshot. Techshot is one of the commercial implementation partners for the ISS National Lab. And Gene is going to present today some preliminary results from recent work with the new BioFabrication Facility that Techshot has installed on the ISS. And he's also going to speak about the future of this facility.
Thanks, Rachel. Techshot has developed a bioprinter and incubation culturing system for the ISS. But listening to Ricky and Nicole's talk, I think it's important to look backward to look forward. So we launched this, as the screen says, in July of 2019. But this project kicked off in June of 2015. So 4 years to get to station, and during that 4 years, in June of 2016, we flew our base printer on a parabolic flight to start to understand how bioinks behave in short-term microgravity. 2017, we flew our bioreactor with freshly printed materials to ISS to take a look to see, are we putting the right stresses? Can we feed them? Can we culture them? Our target has now and has always been cardiac muscle and cardiac tissue. So it's important to add a mechanical stimulation, electrical stimulation, as well as feeding and waste removal. So that's where we kind of tested our baseline bioreactor to get some ideas. And then again, we flew on SpaceX 18. So 12 for the reactor, 18 finally for our full BFF, our bioprinter. And we've tested it now on 18, 19, and 20, and brought it home for some advancement. And I'll talk about that a little bit later at the end of 20. But the reason for us doing this is not an experimental platform. Really, part of this is based on my own passion in the organ shortage. So I'd like to begin with really kind of looking at the reality of the organ shortage. And this is kind of helps where we kind of keep our eye on the ball, that while 95% of Americans claim to support organ donation, only 60% of those people actually register as a donor. But the reality is, even with that, only 0.3% of registered donors die in a way that their organs are donatable. So that equated to about 19,000 donors last year, and 109,000 people currently on the waiting list, 68 of those considered active recipient capable transplants, and another 9 people are added to that list every minute, and 20 people on that list every day die, and others are deemed ineligible to remain on the list. So the catch in the bottom line is, a patient has to be sick enough to be on a transplant list and well enough to remain on that list. And this list isn't getting any smaller. This list is continuing to grow as other attributes in our health system are extending life. We still have this problem of organ shortage, and we're not going to fix it just with donations. So that kind of drove me and drove Techshot through a little bit of pushing to say, what else can we do for looking at organ shortage? So for this talk, I'm going to really kind of dive into the terms that we're using. As you can see with the newness of bioprinting, there's a lot of common language with different meanings. Similar to any technology field. So for us, our bioprinter, when I speak of a bioprinter, it's the collection of dispensers, motion control, imaging system, and software to accurately reproduce a solid model with varying materials or bioinks. The Techshot BioFabrication Facility, or our BFF, uses 4 print heads to build the biological constructs and dispensing through tips roughly twice the size of a human hair. To specifically put cellular and extracellular material where we need it to benefit that developing tissue. I mentioned bioinks. Our bioink is comprised of all the necessary nutrients, proteins, and factors that cells need to both live through the printing process, because that's a little bit rough on a cell, as well as to promote successful maturation given the external cues. In our experience, our cells that we've chosen are all either human-induced pluripotent stem cell or primary cells of vascular nature to push again to a cardiac and nerve and microvascular lineages. And then really where this culminates for us is in the bioreactor. Our bioreactor is designed to recapitulate the chemical, mechanical, electrical properties that a tissue would see in the womb during natural development, but to take that and accelerate it, 10, 100, 500, 1,000, whatever, times faster to form it into a functional tissue. And this is kind of where we go into a story that we like to tell as you look at between a bioprinting and a tissue. It's our when is a pancake story. The bioprinter and the bio ink, that's your pancake batter, and that's what you dispense. The construct you make is the same as pouring your pancake batter into the pan. Nobody really wants to eat that because it's not done yet. It's not done until you have the right griddle temperature and the right flipping, and you keep an eye on it to make that golden brown pancake that we all want at the end. That's where the bioreactor jumps in, is that, constructs are cool, they look cool, but until you get through that bioreacting process, you really don't have a tissue. You have individual cells that aren't talking to each other. You have extracellular matrix that isn't really connected to each other. So an overview of what we looked at for our biofabrication facility is, obviously our goal is to print 3D bioinks to culture them into functional tissues. Why microgravity? Well, bioprinting is hard, so let's try to make it harder. Well, okay, that's not exactly the reason. The real reason is 3D structures are just more easy to produce in microgravity with the absence of convection, with the absence of buoyancy or sedimentation, so we can use a lower viscosity bioink and the cells and nutrients stay where you put them. This is really kind of a paradigm shift in bioprinting where we can print biology only for the sake of biology, not the sake of mechanics. So we don't have to add added cross-linkers. We don't have to add other structures to hold cavities open. We can actually print the 3D shape that we want. And speaking of printing 3D shapes, that's exactly what you can start to do in microgravity that you aren't doing on the ground, is really move to 3-dimensional printing instead of 2.5-dimensional printing. And by 2.5, I mean the way that we typically have done it on the ground, where you're printing layer by layer and building something up, where it's you print XY, you step Z, print XY, step Z. What happens if you print XYZ to XYZ and move that coordinate? Can't do it on the ground, but you can do it in space. And that really opens up to a real 3-dimensional printing to understand how 3-dimensional tissues are made. BFF itself is an L-shaped triple locker. And what that means is it's about 3 feet wide, about 2 feet tall, and about 2 feet deep. It uses a gantry style printer, so X, Y, Z motion control is all held overhead onto the print, onto our smart pumps, and then print down onto a stationary platform. The electronics nitrogen express rack connections are on the right-hand side, which I'll show you in the next picture here. And bioinks are contained in the syringes loaded on the front bracket, which means we can print 4 cell types at a time. We can print 3 cell types and add some other structural element, and those can be rapidly changed out during the printer process. So we're not limited to only 3 cell types or only 4 cell types, because as you know, most tissues in the body are made up of numerous cells in numerous locations and different cell types. And to recapitulate an organ or a functional tissue, you really have to have all that option available to you. And then the culture system is going to be the top right in the image, and it's 3 independent incubator chambers for our specialized bioreactors based on our advanced space processor, which is some legacy hardware that's kind of left over back from when we were supporting space shuttle in our earlier days. So this is what BFF looks like. Again, left-hand side is the print chamber. That's roughly a 18-inch wide by 2 foot tall, and can print nominally in a our bioreactor gives it really about a 3-inch by 3-inch by 2-inch space, which doesn't seem like a lot until you're bioprinting and realize that that's a huge volume for bioprinting. And then our ADSAP on the top right and the electronics on the bottom left. Jumping inside the printer, this is kind of where the magic happens. It's, you can see on the left image, we have the 4 color-coded smart pens. Each one of those will have its own syringe attached to it to dispense. And down below that is the dock. On the right-hand view, that dock is populated with our bioreactor, and 2 of the pumps are loaded with syringe holders. Looking at our initial bioreactor design, or actually right now our 3rd generation bioreactor design, it has everything that you would anticipate for making a cardiac tissue. You have a feed and waste medium bag, so you can pump in and control it because we want a high automation on our system. We have a camera system to watch the evolving tissue and to watch how it's responding to stimulation, as well as a reactor that will control the chemical, the mechanical, and the electrical stimulation. So in there, we can provide plus or minus 20% strain on the tissue. We can provide voltage spikes to go with that strain, so we can start maturing tissues in the direction we want and start really understanding how those tissues are maturing and what capability we have in microgravity that we didn't necessarily have on the ground. So the efficiency of our bioinks, because we're going biology for the sake of biology, we kind of reinvented bioinks in-house, or not necessarily reinvented them, but kind of went back to, just the base components and just to take a look at it. So the result is on the ground is our beating cardiac tissue test. So these are iPS cells that are pushed in our bioreactor to a cardiac lineage and then pushed to maturation. And you can see they start to beat, they start to look like what everyone has seen before in cardiac tissue development. On the right-hand side, what we can see is two pictures of our decellularized matrix. Again, because we're printing the human heart and we're looking at a neonatal development, we're looking at neonative tissues. So we're looking, in this case, at umbilical cord and placental tissues that are decellularized, treated to remove any viral or bacterial components, and then they go through a process to take those tissues through a lyophilization, through a cryomilling, and then through a resolubilization down to form an ink. These inks are then mixed, in this case, with a cardiac tissue ink that's processed the same way, and then a little bit added collagen just as a bulking agent to form what we're using as our primary inks. And these inks, again, have a viscosity that's too low to print directly on the ground. So what we learned? Well, what we learned is about the same as you've always heard from Elon, is that space is hard. Real-time control that you have in the lab, when you add a 6-second delay in a split communication system, is not the real-time control that you know when you do it on station. Simplifying systems to improve containment of materials can change biology, through changing an orifice, changing a valve size, changing a seal. All these things will affect the biology since it's moving past it. And there's never enough time when working on the ISS. This even in our early studies led us to look at higher speed motion control systems. So now BFF is built around linear motor systems with capable driving at over 700 millimeters per second, because speed is really the essence. And then we have to look at dispensing capabilities that can process at those kind of speeds, because we don't want a long wait between the time that we start a tissue and the time that we finish a tissue. Speed kills in some aspects, but slow speed is actually, in our case, worse than a fast speed. And then we need to relearn fluid mechanics. Shapes matter most. When you get rid of buoyancy, when you get rid of cementation, when you get rid of all the gravity effects, now you really, really have to understand surface energy. You really have to understand your fluid mechanics of cohesion within the fluid itself, because surface chemistry, surface factors, surface energy drive what's happening in your fluid. So now you need to change your materials, add shapes that both can pin materials and cause materials to flow, because our bioreactor is printed empty. We print in an empty bioreactor and then we have to fill it with media. Air bubbles don't float to the top in space the way they float to the top everywhere else. So you have to understand, how do you push the air out and push the media in and have that fill in a manner that your tissue doesn't end up with air gaps around it that will cause it to die, and also just to make sure that you have a system that can fill completely. And what we've learned through our 4 flights now is keep trying. This is an iterative process, and this is where Cases in the National Lab really comes in as a great partner in this process for us, because it gives us the ability to keep trying, keep flying, keep working on it. Again, because we have the ability that we're an implementation partner ourselves, it gives us a little bit more flexibility to fly, because I'm flying on my boss's dime and not flying on a NASA grant or not flying on a contract. He doesn't always like that process, but that's kind of the way it works. And, we have this great ability to keep trying. And so kind of moving forward, we've decided there's some things that we could change. There's some things that can make this better for us. One of those things is an enhanced thermal control. If you noticed, even in Ricky's talk, he's talking about looking at thermal control at the pen level. It's something we didn't have in our original bioprinter that we're bringing into the printer for going back up, because as you change materials, it really matters what temperature they're kept at during the printing process. No matter how fast your printing process goes, if you put them into a 37-degree chamber, they're going to reach 37 pretty quick, even through conduction without convection. We're updating the bioreactor to take advantage of the surface tension issues that I've spoken of before, using surface tension as a restraint to add in strong cuts, to add in pinning edges, so that we can build more easily and not have a material flow off of a surface, not because of gravity, but because of shape and surface chemistry. Again, still working on improving our pumping and our filling systems. Again, that's an iterative process to say, how do we fill a bioreactor and void the air as quick as possible? And then our current system is based on a white light system, and we're adding UV cross-linking because we know as we open this up to commercial use and other partners that they may want to use a cross-linkable ink that's currently available. They may want to use the same ink that they're using on the ground, and we just are expanding our capability to meet the needs of our customers, because when we fly back, I'm not going to be the only customer. It's not going to be the Techshot science team's project continuing forward. It's going to be the Techshot science project, as well as open for business for anyone else that wants to print in our system, that wants to culture in our system, and understand how their inks, their designs, their materials work in microgravity, and really reduce that overhead cost. Ricky's talking about earlier how expensive it is to build your own printer. Well, this is kind of our approach to it, is that we can open this printer up to let other people use it, other people test it, other people bring more materials in, because while my focus is going to stay cardiac, there's a lot of organ shortages, there's a lot of other materials, there's a lot of ink development and bioprinting development that needs to happen. So with that, we're going to be open for business after we return flight, which is now looking like the NG16 flight, July of 2021 estimate. So we have about a year before we're back up and ready for business. And with that, I would just like to thank everyone for participating. It's great to see this number of people for an online session, and thank our teams at the left picture with our Techshot facility in Indiana, and our right side with our lab down at the Kennedy Space Center. Thanks.